From complex stroke mechanisms to the simplicity of arithmetic Part 2, number 1572, March 13, 2026, Gerald C. EclaireMD Foundation. Category: Mathematical Simplicity and Medical Sophistication. Section 3. Difference between scientific modeling and typical medical risk scores. Most traditional medical risk models rely on statistical scoring systems. In many medical studies, medical professionals calculate disease risk by adding together several different influential factors. Each factor contributes a certain amount to the final score using different weighting factors, and the total score is obtained by adding them together. These simple linear models typically take the form: risk score equals A1 asterisk F1 plus A2 F2 plus A3 asterisk F3 plus, where F1, F2, and F3 represent different risk factors, and A1, A2, and A3 represent the weighting assigned to each factor. This approach is useful for population studies. It estimates the probability that a group of people may develop a disease over many years. However, additive statistical scores do not describe the physical mechanism of system failure or the real condition of a specific patient, although the two equations may look similar. Their logic is very different. The additive model is written as risk score equals A1 asterisk F1 plus A2 asterisk F2 and plus A3 asterisk F3 plus. In this additive model, each factor contributes independently. The total risk score is simply the sum of the contributions from each factor. In contrast, the TSI model uses multiplication. TSI tilde factor 1 asterisk factor 2 asterisk factor 3. In this structure, the factors interact with each other. If one factor increases, the result increases. If two factors increase together, the effect becomes much larger. This reflects the interaction between variables in real biomedical systems. In engineering and physics, system behavior is usually modeled differently. For example, mechanical failure models often take the form: failure risk approximately equals structural vulnerability multiplied by applied load multiplied by environmental damage. This structure is multiplicative because the variables interact. The TSI model follows the same scientific principle. TSI equals PP multiplied by SBP multiplied by AG. This is not a statistical association model. It is a mechanistic interaction model. Section 4. Viscoplastic energy and calculus. Another important mathematical framework used in my research is viscoplastic energy (VMT) or VPT modeling. In viscoplastic theory, system behavior is described through relationships between stress and strain. One key concept is strain rate. Strain rate equals change of strain divided by time. In mathematical form, strain rate equals d epsilon strain dt times stress is then related to strain rate through viscosity. In simplified form, stress equals the strain rate multiplied by the influential input factors. When an external load is applied to a system, stress and strain interact. The relationship between these two variables can be illustrated using a stress-strain diagram. The area enclosed by the stress-strain curve represents the amount of energy generated from stress-strain interactions. To calculate this area accurately, calculus is used. Calculus is a mathematical tool for analyzing continuous change. It involves operations such as division to measure rates of change, derivatives, and summation of very small elements, integrals. An integral can be interpreted as adding many very small pieces together to calculate a total quantity, such as the area under a curve. In viscoplastic analysis, energy is calculated as energy equals integral of stress y-axis with respect to strain opening parenthesis x-axis closing parenthesis. Compared with simple statistical scoring methods, viscoplastic modeling requires more advanced mathematical tools such as rate analysis, continuous functions, integral calculations, energy estimation. These tools are commonly used in physics and engineering to analyze system behavior under load. In my research, viscoplastic energy analysis helps quantify how pathophysiological stress accumulates over time and how it interacts with pathophysiological structures. Conclusion: the development of the TSI model rose from a practical need, preventing a second stroke. By combining continuous pathophysiological monitoring with mathematical modeling, I created a simple indicator that reflects the interaction between vascular mechanics and metabolic stress. The comparison between TSI2 and TSI3b demonstrates an important scientific principle: blood pressure alone does not determine stroke risk. Metabolic factors such as glucose can amplify vascular vulnerability. This interaction is captured through multiplication, consistent with the scientific principle illustrated by Isaac Newton's equation F equals m*A. Real-life systems are rarely linear. Interactions dominate. Viscoplastic energy modeling further extends this idea by using calculus to analyze stress, strain, and energy accumulation in complex systems. The purpose of this research work is not theoretical elegance. It is practical survival, maintaining control of stroke risk one day at a time through measurable data and simple mathematical models. Truth in science comes from observation, measurement, and logical reasoning. The equations and data should speak for themselves. By contrast, applying Newton's simple arithmetic equation format, the TSI model behaves like an engineering failure model, something medicine rarely adopts but desperately needs. I have moved away from population averages, which can be misleading for individual application, and toward individual physics. Furthermore, this model was inspired by Newton's law of motion and makes the TSI highly sensitive to spikes. A 10% increase in glucose combined with a 10% increase in SBP results in approximately a 21% increase in TSI3B 1.1 * 1.1 equals 1.21. Whereas an additive model would show only a linear 10% increase, 1.1 plus 1.1 equals to 0.2 to 0.0 equals 1.1. This hypersensitivity is exactly what a post-stroke patient needs for an early warning system. It transforms the patient from a passive observer of their health into an active systems engineer of their own body. Figure illustration: monthly averages of TSI2 and TSI3B March 2025, March 2026. This figure presents the monthly average values of two stroke risk indicators, TSI2 and TSI3B, over a one-year period following a hemorrhagic stroke in June 2025. TSI2 reflects vascular mechanics only, calculated from pulse pressure PP and systolic blood pressure SBP. TSI3B incorporates an additional metabolic factor, estimated average glucose E, to account for long-term vascular damage from diabetes. After the stroke, TSI2 shows a steady decline, indicating improved blood pressure control through lifestyle interventions, such as breathing. Emotional stress control. In contrast, TSI3B declines more slowly and eventually rises again, reflecting persistent metabolic stress and elevated glucose levels after stroke event. This divergence highlights the nonlinear interaction between mechanical and metabolic factors in stroke risk. It reinforces the importance of glucose management alongside blood pressure control, as captured by the multiplicative structure of the TSI3B model. Final reflection: this paper can also be viewed as part of a long scientific lineage. More than 400 years ago, Isaac Newton showed that complex physical systems could often be explained by very simple mathematical relationships, such as his famous law of motion, F equals m*A. Centuries later, around mid-1960, Professor Norman Jones at MIT expanded Newton's physical thinking of viscosity into structural mechanics through sophisticated viscoplastic energy modeling, using calculus to analyze how stress, strain, and energy accumulate in materials under dynamic loading. By combining a few measurable physiological variables, pulse pressure, systolic blood pressure, and glucose exposure, the TSI model uses simple arithmetic relationships, relying more on multiplication and division than on addition and subtraction, to represent the interaction between vascular mechanics and metabolic stress and stroke risk. Viewed in this way, the conceptual trajectory runs from Newton's simplicity of physical law through Jones's advanced viscoplastic energy modeling, and then back to the simplicity of my TSI stroke risk framework presented here. This arc illustrates a common theme in science: complex systems can often be understood through simple mathematical relationships after sophisticated applications, as long as the correct interacting variables are carefully identified. The trajectory I described above is intellectually consistent. Newton's simple physical interaction logic and sophisticated viscoplastic energy engineering modeling. So, return to simple arithmetic interaction for biomedicine's pathophysiology. This complexity greater than deeper complexity and sophistication, simplicity again arc is actually very common in science. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or published as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.